This is a screencast on significant figures in chemistry. We may not get through the whole thing, we may have to break it up into parts. So in chemistry, what we're really concerned about is measurements. We haven't gotten there yet, we haven't talked about numbers, but we will, and this may push some of you to the edge of numberness. So uncertainty in measurements. So it's important to realize that any measurement will always contain some degree of uncertainty. The uncertainty of a measurement is determined by the scale of the measuring device. The smaller the unit you use to measure with, the more precise the measurement is. So we talk about precision and accuracy. Precision is how close individual measurements agree with each other, or it's sometimes called repeatability. Can you get the same measurement again and again? And accuracy is how close an individual measurement is to the true or accepted value. So on these dartboards, I know if you know the real game of darts, this is not true, but we'll just accept that the true value that you want to get on a dartboard is the bullseye in the center. So to be accurate, you would have to hit the bullseye. But to be precise, you'd want to hit any spot, the same spot, again and again. So this first picture here, if you take a look at it, shows high precision because the same place was hit again and again, but it's low accuracy because accuracy would be hitting the bullseye. This one is low precision with high accuracy. I don't know if I'd call this high accuracy or not, but getting closer to the bullseye is accurate, but it's not precise because it wasn't repeated. The darts are all over the board. And this one is low precision and low accuracy. They're all over the board. They're not close to the bullseye. And this one is high precision because the darts were thrown again and again relatively to the same place, and it's accurate because it's at the bullseye, which we consider to be the true or accepted value. So when we do measurements in chemistry, we are concerned about these uncertain digits, and the uncertain digit is usually the last digit written in a number. So if you look at this ruler here, here is a ruler with a pencil. You know for certain that it is at least 9, and these are centimeters, and it looks like it's about there, which is halfway between 9 and 10, so you know that it's 9 and a 5. So you would say 9.5, and then you have to put one last digit on there, which would be your guess digit. So you would say 9, because you know that for certain, and you know it's a 5, because it's at least there. And then your last digit has to be the guess one. It looks like it's not more than the 5, meaning that 5, or less than the 5, so I would call it a 0. So really and truly, that number could be 9.51 or 9. Pen's not working so well, 9.49. So it could be plus or minus 0.001. So that last digit could be up 1 or down 1, and that one is your guessed or estimated digit. Now let's try measuring some of these items here. And we're going to look at this item there and measure it according to ruler A and ruler B. So if we were looking at ruler A, it looks like it's right about here. So it's between the 4 and the 5, but it's closer to the 5. So we would know it's a 4. I think these are centimeters again. And it looks closer to 5, so I'm going to say 4.8. 8 is my guessed digit on that one. But if we measure it according to ruler B, we definitely know that it's 4. Looks like it goes clear over to the 8th mark. So it's definitely 4.8. We know those two for certain, and the last digit is the guess digit. It looks like it's pretty much on there, so I'm going to call it 0. That again is my guess digit. It could be 4.81 or it could be 4.79. So this ruler B, gives us a lot more precision for our measurement because we have a lot more detailed information. So in chemistry, you want to really be careful about what instrument you're using to measure with. And a lot of times we measure with scales. You really want a scale that has a lot of good detail to it. A good scale, though, that goes out past, I would say, 2 decimal places gets to be quite expensive. In fact, we only have one scale in here that goes out to that decimal place. Very, very expensive. So you know with a good piece of technology that's going to give you good results, it costs more money. So let's look at the measurement of this graduated cylinder. So when you measure liquids, you always do the bottom of the meniscus. And here, the meniscus, you can see it there. So I would say this measurement it's between 60 and 70. In fact, it's a little more than halfway, so that's 65. And it looks like it's at about 66, so I would call that 66. We know it's 66, and my guess digit is going to be the last one, which is 0, so 66.0 milliliters. You always have to be careful of the gradations on a graduated cylinder. Sometimes each mark is 1, sometimes it's 0.2. It can be tricky. Now we're going to move on to scientific notation. I hope you've done this in some of your math classes. But in general, scientific notation is a way to write really large or really small numbers. And this is the general format, m, which is some number, times 10 to the x, and x is the exponent. M is any number between 1 and 9. In other words, it can't be point something, like 0.1 something, and it can't be 10 point something. And the exponent x, if it's a positive, it means the number is larger than 1. And if the number is negative, it means the number overall is less than 1. So if you were to have the number 10,000, you wanted to write it in scientific notation, the decimal place, you need to put it between the first digit you see on the left and whatever numbers are after it. So that would go after the 1. So it's 1 times 10 to the 4th, and it's 10 to the 4th because it's 1, 2, 3, 4 places to the right is where the decimal really started. So that 10 to the 4 means you'd move the decimal 4 places to the right to get your number. Now on this one, the decimal is there, but to put it in scientific notation, we go 1, 2, 3 slots over. We have to put it right after that 2. So it would be 2.578 times 10 to the 3rd. Here are a couple more examples of scientific notation. So these two numbers are less than 1, and in this one, it's 0.00215. Putting that 0 in front of the decimal isn't necessary, but it really is important, and it helps you realize the magnitude of the number. So this number, you want the decimal to go right after that 2, and that would be 1, 2, 3 spots it would move, so 2.51, and that minus 3 means that the number is less than 1. And on this one, the decimal place would move 1, 2, 3, 4, 5 places, so 5.7 times 10 to the minus 5th. Now what is not acceptable is like 0.1 times 10 to the minus 1. So you cannot have this first number be less than 1, and this wouldn't be acceptable either, 12.2 times 10 to the 3rd. Yes, you could write it like this, but it's not acceptable scientific notation. That decimal would have to be between the 1 and the 2 to be acceptable. Now we're going to start with significant figures, and I often call them Sig Figs. There are about 3 rules to Sig Figs, and some of these may confuse you or frustrate you. There is the 0 rule. The 0 rule is the frustrating one. So let me backtrack and talk about some numbers just to begin with so you know what I'm talking about. So if I were to give you the number 1, 2, 5. When I ask for significant figures, I'm asking for digits that count. And the digits that count in here are the 1, the 2, and the 5. And so you count them up 1, 2, 3. There's 3 digits. So you would say there's 3 significant figures. So if I added a 6 and a 7, your number of sig figs would go up to, let's see, 1, 2, 3, 4, 5. You'd say 5 significant digits. So any digit between 1 and 9 counts all the time. The one digit that can be a problem is the 0. Zeros can be problematic. So here we got the rules for the zeros. Leading zeros are never significant. Now what is a leading 0? A leading 0 is a 0 over here just flat out holding a place, because you could write that number in scientific notation and then the zeros wouldn't be there. So that number could be written as 5 dot, or maybe not even a dot, 5 times 10 to the minus 1, 2, 3. So there, the zeros aren't there. They're really just holding a place. So leading zeros, those zeros over here, never count. Now we move to embedded zeros. Embedded zeros mean zeros that are held captive or in the middle. They count all the time. So in this number, you'd say there's 1, 2, 3, 4 digits. The 2 5s count and the 2 zeros count because they're embedded. Trailing zeros are only significant if there's a decimal point specified. Now what? So example, if you had 5.1300, all of those digits count because there's a decimal there. That decimal makes those trailing zeros count. So what is a trailing zero? A trailing zero is a zero at the end of a number somewhere. But if you have the number 500, there's no decimal place there. The 5 counts, but those 2 zeros don't count because there's not a decimal place there. Now, what is not a trailing zero? Some people seem to think that a number like this, it does have trailing zeros. My pen just isn't working well. Those are the trailing zeros. Those are leading zeros. Leading zeros never count, so those wouldn't count. But since there is a decimal there, it means that that 5 counts, that 0, and that 0. So there would be 3 significant figures there. And then we move on to some rules about addition or subtraction. Those are lumped together for doing math with significant figures, and multiplication and division is lumped together. And we will move on, practice counting our sig figs here for a moment. Before we practice some sig figs, we're actually going to talk about line over the zero. In chemistry, and I think it's only in chemistry, we get this weird thing, a line over a zero, and it does not mean a repeating number like it does in your math class. What it means is that that zero counts, it's significant. So if that zero counts, that zero next to it is now captive and it counts, and then those 3 digits count because they're not 0 digits. So you have 1, 2, 3, 4, 5 significant figures. That last 0 doesn't count. And this seems like a real silly way to do things, but sometimes with certain numbers, like a number like this, it's easier to write it like that. You could write 1.7500 times 10 to the 5th, but really and truly, it's easier to write it like this. And then you see visually that that line over there makes that 0 count, that last one doesn't count. And what does this all mean again? That tells us how precise or accurate our measuring device is, how many divisions it has when it's measuring. And we don't have a unit on this, so we don't know what exactly it's measuring, but more significant figures usually indicate more precise of an instrument. Rounding in chemistry. So you got to be able to round, and for the most part it's rounding like in other classes, but it can get a little confusing. So if I were to ask you round the following numbers to 3 significant figures, so you have to be able to count 3 sig figs. So we have the 1, the 3, and the 2. Those are our first 3 sig figs, and the way to make something not count as a sig fig is to turn it into 0. So that 3 then would become a 0. So it's 1, 3, 2, 0. So now we have 3 sig figs. Now this next number, again, we're going to keep the 1, the 3, and the 2, but our last digit is a 7, and that 7 would actually make that 2 round up to a 3. So it would be 1, 3, 3, 0. Now let's round this one to 3 sig figs. So it's going to be the 6, 5, and the 2. Look at the number next to the 2. It doesn't affect it or impact it. So it's going to be 6, 5, 2, and then we change the rest of those into zeros. If you got rid of them, you wouldn't have the same number. It still has to be reflective or close to the same number. So 652,233 is close to 652,000. Now this number, if we round it to 3 sig figs, we got the 2, the 7, and the 7. Now look at that 8. That 8 is going to make that last 7 become an 8. So 2.78 times 10 to the second. 3 sig figs here. 1, 2, 6. That 7 is going to make that 6 turn into a 7. So 1, 2, 7, and then the rest of them are zeros.